Hello, I'm Maxime Lègues, and in this presentation I will introduce you the world's first 3D bioprinted skin model suitable for screening drugs and ingredients for normal and inflamed skin. Immune system is involved in many skin disorders such as atopic dermatitis, psoriasis, infections, or acne. The 3D immunized skin model has been developed in order to enable cosmetics and pharmaceutical companies to test and screen ingredients on more suitable and physiological human reconstructed skin. Although it allows testing on different skin disorders, toxicological studies can be carried out. First of all, human cells were dissociated from a human skin donor. Human primary isolated cells were then amplified before being mixed with a suitable bioink and 3D bioprinted using pneumatic extrusion. 3D bioprinted models are then mature over time and can be used for ingredient testing. We always work on development and optimization of our model because we want to obtain good skin models and better mimic real skin tissues. We decided to use 3D bioprinter to increase reproducibility between the different models. Indeed, identical models will be produced compared to manual models, which includes human variability between each reconstructed tissues. More than 100 skin models have been printed in an hour, a ratio not reachable with manual skin models. It will also improve the effectiveness of the tissue by printing cells layer by layer with a printing resolution of 200 microns. For example, the extracellular matrix mechanics, such as matrix stiffness, can be adjusted according to different bioinks. It is even possible to increase the cell organization and development by playing around different printing parameters such as pressure, speed, temperature, and many more. You can also personalize each model using a computer-aided design software. This is important to adapt the model and allow to produce on-demand accurate models. In order to recreate 3D humanized skin models, we combine our knowledges on skin with isolated immune cells from human blood donor. We first isolated peripheral blood mononuclear cells before performing a CD14 positive selection and keep only monocytes. To obtain more suitable immunized skin models, two different populations were differentiated. On one hand, M1 macrophages, more related to pro-inflammatory responses. On the other hand, M2 macrophages, involved in anti-inflammatory processes. Once the human primary cells were isolated, we amplified the different cell types such as keratinocytes, fibroblasts, and macrophages. The amplification phase can vary between donors, especially because of the age or the location of the skin surgery. During this step, monocytes were differentiated into the two macrophages populations thanks to different growing factors and interleukins. To better screen the two macrophages populations, M1 and M2 were analyzed on flow cytometer. Several screening markers such as CD80, CD163, and CD206 were used. As we can see, M1 macrophages population was more differentiated than M2 population. Once all the different cell types were amplified and differentiated, 3D models were bioprinted according to the designed template. Then, models were matured in the incubator during 21 days, and it is possible to notice that at the very beginning, models looked more transparent while they become darker and darker with days thanks to the cell development and the cornification of the epidermis. To ensure the good development of the 3D models, viability testing was performed all along the maturation phase. As we can see here, the viability of cells was good at day 7, whether some of them started to die at day 21. Over time, macrophages became bigger and bigger. Indeed, it was possible to observe big round cells on live dead imaging at day 21. When models were mature, we observed the development of the bioprinted tissues and cell organization using histology stainings. On the top of the screen are results of hematoxylin, eosin, and saffron stainings, while immunofluorescent staining is located at the bottom of the screen. To reveal macrophages in the model, CD68 staining was performed, appearing in green on the image. To shed light on inflammatory responses, models were stimulated with lipopolysaccharides, so-called LPS, and as we can notice, models look more irritated and damaged. We can even notice that some macrophages migrated toward epidermis in response to the stimulation. To better demonstrate macrophages activity, several human inflammatory cytokines were measured by ELISA tests. Secreted TNF, interleukin-10, interleukin-1 beta, and interleukin-8 were quantified on 4 different conditions. On the left side of each graph appears normal 3D skin condition made of fibroblasts and keratinocytes. This condition was to check the basal level of each cytokine without immune cells. Just at the right, there is the normal 3D skin condition, including macrophages, but not stimulated. The concentration of each cytokine remained very low compared to the third condition, the 3D skin model, including macrophages, but this time under LPS stimulation. Following this stimulation, it is possible to observe an increasing level of each cytokine produced. Finally, to confirm the efficiency of the model, inflammation was induced on immunized skin models before being treated with dexamethasone, which has an anti-inflammatory effect. This condition is a positive control of treatment and allow to observe the decreasing level of inflammatory cytokines. To briefly summarize the key points of this presentation, we developed a 3D skin model, including macrophages, which showed over time a good viability and responded to inflammation. This model has been designed and developed using a 3D bioprinter in order to be more reproducible and rebuild a more effective tissue. We also find out that pro-inflammatory models, including M1 macrophages, were easier to obtain than M2 cells. Indeed, M2 macrophages are delicate cells and not so robust as M1 models. Moreover, in response to inflammatory induction, macrophages migrated toward epidermis, which is a normal and representative process of atopic dermatitis. It is important to remind that working on human primary cells induces variability, and the quality of the full skin model impacts the human skin models. Nevertheless, our 3D humanized skin model is now available for cosmetic testing. We are still working on the development and optimization of our 3D bioprinted immunized skin model. We are now developing an in situ maturation phase in order to optimize our M2 system. We are also currently assessing different inflammatory cytokines in order to reinforce the robustness of our model. Specific macrophages stainings is now ongoing to screen and differentiate both macrophages populations after the maturation step. This could also allow to visualize how the model reacts and adapts following ingredient testing. Obviously, we developed and made this model available to perform cosmetic and pharmaceutical testing. We want now to use this model to assess different products and ingredients and show its effectiveness. Last but not least, we are diversifying our skin catalog by complexifying with neuron cells, pigments, and vascularization. Indeed, we want to propose a more suitable model designed for all the different applications. This is already the end of the presentation, and I would like first to thank you for watching. I would like to thank all the team at CTIBIOTECH for their support, for their help, and for all the work they're performing every day. A big thank to the BASF team as well for their contribution of the development of the 3D bioprinted immunized skin model. And I cannot end this presentation without giving many thanks to the organizers of the IFSCC 2020, an edition we will remember. Take care and stay safe.